Hello everyone and welcome back to the channel. In today's video, we will start our second topic of O-Level Physics 5054, that is kinematics. First, let's start with the very definition of the word kinematics. Kinematics comes from the Greek word kinema, which means to move. Now, in physics, kinematics refers to the branch of physics that is concerned with the motion of objects without taking into consideration the forces that bring about that motion. What this means is that while we are studying about the motion of the object, we are not actually considering what is causing that motion, that is, which forces are actually causing that motion. And this is quite important because this is what separates kinematics with dynamics. Because in dynamics, we study motion with reference to the forces, but in kinematics, we are only concerned with the motion itself. Usually though, both are taught at the same time because it is very hard to separate kinematics and dynamics completely. However, for this video, as you would be concerned with the very basics of kinematics, I've kept only to kinematics and decided not to touch the forces part at all. So, without further ado, let's begin. Before we dive into the complexities of kinematics, there are certain terminologies that we need to understand completely. Some of these you would already be familiar with, but it is always good to clear all our concepts. The first one, and starting off completely easy, is simply speed. Now, speed is further divided into two categories. We have instantaneous speed and average speed. So what's the difference between the two? Well, instantaneous speed refers to the speed of an object at a particular moment in time, whereas average speed is simply the mean, or as the name suggests, average speed of the entire journey. What this means is basically if we are traveling at an average speed of 60 meters per second, it means that in our entire journey our mean or average speed was 60 meters per second. However, that does not mean that for the entire journey our speedometer of the car showed 60 meters per second. It is possible, obviously at some point we might have slowed, at some point we might have gotten faster than that. So if I say what was the speed at exactly 40 seconds, then you would be giving me the instantaneous speed, and that would be the one that is shown by the speedometer at that particular moment in time. However, our average speed, that is the total distance divided by total time for our entire journey, is called the average or the mean speed. Average speed, I'm pretty sure we have all considered many times in our maths and science questions, but here is just another question for the sake of revision. Here, the distance traveled is 360 meters. The time taken to travel 360 meters is 40 seconds. Another important thing to notice here is that whenever we are given a question of calculating speed, we must always calculate the speed in meter per seconds. So let's say if the distance was not given in meters here, or let's say if it was given in kilometers, we would have to convert the kilometers into meters, and whatever time was given, we would have to convert it into seconds. Sometimes, however, the examiner explicitly states that you can give your answer in kilometer per hour, and at those times, obviously, it is not necessary to convert. But if the question does not say in which units you have to give, you have to assume that they want in meter per second, because as you can see, the SI unit of distance is meters, and of time it is seconds. So we have to give speed in meter per second. I'm sure you probably have already calculated the speed by now. Yes, it's definitely 360 divided by 40 seconds, and so the average or the mean speed for the entire journey is 9 meters per second. Next up we have acceleration. Now acceleration is defined as change in velocity in a given time period. In other words, acceleration is the rate of change of velocity. It is represented by a small a, and as we know in physics, it is always important to write the correct case. So here, a is in lowercase, so we would always write acceleration as a small a. Now, here's something that would come as very useful in both sciences as well as maths. Like I said, acceleration is defined as the rate of change of velocity. Now, whenever we say the word rate of change, it means that whatever we are calculating the rate of change of, we would divide that by time. This is a given thing which is always going to be true. Whenever we are talking about the rate of something, we would be dividing that something by the time, whatever that thing is. So here, for example, as we know, the acceleration is the rate of change of velocity. So we would be dividing velocity by time. And this actually gives us the reason why the unit of acceleration is meter per second squared. Can you see why? As we know, the unit of velocity is meter per second. So basically we are dividing meter per second by second. So using simple maths, this can be written as meter per second squared. The formula for calculating acceleration is quite simple. As you can see, like we said, acceleration is the change in velocity in a given time. So here the formula for the acceleration is change in velocity upon time taken. First, we have to, however, calculate the change in velocity. And to do that, like always, whenever we are calculating a change, we subtract the initial value from the final value. So in other words, I can write the formula of acceleration as final velocity minus initial velocity upon time taken. Again, like I said, whenever we have to calculate a change of any quantity, we would always do it like this. For example, if we have to consider the change in the distance traveled, we would go with final distance minus initial distance upon time taken. So whenever we have to calculate the change between two objects, we subtract the initial value from the final value. So a for acceleration is equals to final velocity minus initial velocity upon time taken. Let's solve a quick question for this so we can know that we have aced our acceleration topic. A cyclist traveling at a speed 15 meter per second accelerates for 5 seconds and reaches the speed 30 meter per second. Calculate the average acceleration of the cyclist during that time. If you want, you can pause the video here and try to work this out by yourself before seeing the solution if you cannot do it, or if you have done it, to make sure you have got the right answer. Well, let's see how to do this. Now, first we should always start by making a data table. What this means is that we should see which quantities have been given in the question and what we can deduce from that. So here I have got the data table done. We can see that the initial speed they have given us is 15 meter per second because a cyclist was traveling at the speed 15 meter per second. The final speed that he has reached, as given in the question, is 30 meter per second. So, and the time it took for the cyclist to go from 15 meter per second to 30 meter per second was 5 seconds. These three quantities have been given in the question, and as we know that using these three quantities we can easily calculate out the acceleration. So here a is equals to the final speed minus initial speed upon time taken. The final speed is 30, the initial speed is 15, and the time is 5. So putting it in the formula, we have 30 minus 15 upon 5 is equal to the acceleration. In other words, simplifying that, we get 15 upon 5 and which equals 5 meter per second squared. So our acceleration in this question was 5 meter per second squared. Our last topic for today is motion time graphs. Now, motion time graphs are actually quite important in kinematics because they are a very good way of showing the entire journey of an object. Here are some key points regarding motion time graphs. Motion time graphs can include both distance time and speed time graph. Notice that always the time will be plotted on the x-axis and the distance or the speed/velocity would be plotted on the y-axis. This is because time is an independent variable, whereas distance and speed, as they depend on time while calculating them, is the dependent variable. And always in maths, we plot the independent variable on the x-axis and the dependent variable on the y-axis. For distance time graphs, the gradient of the line gives the speed. I am sure you are familiar with the concept of gradient in mathematics. It is the change in y divided by the change in x. We will look at more examples in the future, but for now we should just know that the gradient of the line in a distance time. Notice we are not talking about a velocity time graph here. This is only true for the distance time graph. That in the distance time graph, the gradient of the line gives the speed. Now talking about velocity time or speed time graphs, we have that the gradient of the line in speed time graphs gives the acceleration of the object. So while the gradient in distance time gave the speed, in speed time or in velocity time graphs, the gradient of the line is now equal to the acceleration of the object. Lastly, the area under the speed time graph gives the distance traveled by the object. What this means is that whenever we have a line across a graph, we can calculate the area that between the line and the x-axis, and that would be equal in this case to the distance traveled by the object. I know this sounds a bit complex, but let's look at this example here. So on the screen, as you can see, we have got a speed time graph. Time, as I said earlier, is on the x-axis, whereas the speed is on the y-axis. Now, first of all, let's go with the basic analysis that we can do from this graph. We can see, let me actually turn on the screen pointer for this one. We can see that between 0 and 20 seconds, the speed gradually increased from 0 all the way to 10. So our speed went from 0 all the way to 10 in 20 seconds. Then for the next 20 seconds, it stayed constant at 10 meters per second. So we accelerated at the start, then our speed became constant. As you can see, till 40 seconds, it has become constant. Then, in the last 10 seconds, between 40 and 50 seconds, we decelerated quite quickly from 10 all the way again to 0. So in a way, we can say that our car, let's say it's a car, it started from rest, it accelerated to 10 meters per second, it stayed at that speed for 20 seconds, and then it decelerated quickly and came back to rest. Now, applying the key points that we learned here, we can see that this line right here, we can calculate its gradient, and as we know, in speed time graphs, the gradient of the line gives the acceleration. So using this figure, it is possible for us to find the acceleration of the object. Can you try? Well, as we know, for a straight line passing through origin, it is very easy to calculate the gradient. We can do so simply by dividing we can select any coordinate here and divide its y coordinate by its x coordinate. So for example, if I talk about this point right here where the curve turns, here our y point is 10 and our x is 20. So if I need to calculate the acceleration of this line or this journey, we can calculate it by simply dividing 10 by 20, and we get the acceleration as 0.5 meters per second squared. So our acceleration for this journey, for this car from 0 to 20 seconds is 0.5 meters per second squared. From here to 40, notice that the line is horizontal, which means that the speed is constant. This is another concept we learned earlier. What happens when the speed is constant to the acceleration? Well, as you can see, acceleration is the change in velocity. When the velocity is not changing, there is no acceleration. So between 20 to 40 seconds, as the speed is constant, our acceleration is 0. You can further check this if you want to see how this works. You can also calculate the gradient. This would be a nice exercise to see exactly why the gradient rule works. If you calculate the gradient of this straight line here, you would see that the gradient also comes 0, which means that there is no acceleration. Between 40 to 50 seconds, however, the graph is going down, and is going down much more steeply. So the difference here and the difference here is, number one, as you can see here, we are going upwards. The slope is inclined upwards, whereas here the slope is going downwards. What this means is that while this was acceleration, here we are decelerating, and it also makes sense because we are going from a higher speed all the way to a lower speed. So we went from 10 to 0. That means that we decelerated. And here's another thing that's very important here. That is, as you can see, we calculated the acceleration here. But if I just asked you without using any numbers, can you tell me whether this acceleration was greater or whether this deceleration is greater? Can you tell me which one of these was greater? Well, there's a very nice trick to do so. And the trick is, we see which slope is more inclined. This slope it has a quite normal edge. It's not like it's going straight upwards or like much too upwards or much too downwards. It's going upwards quite normally. This one, however, has a very steep slope. This means that it is coming down much faster than this one. So even without considering any values, we can tell that the gradient of this slope would definitely be much greater than this one. Obviously it would be in minus because this is deceleration, but here we are only talking about the magnitude, and the magnitude, that is the rate at which the object is decelerating, would be in this case much greater as compared to the rate at which it accelerated. Lastly, we can also find out how much did this object travel in this entire journey. And to do so, there are a number of ways, but let's start off small. What I'm going to do now is I'm going to divide this entire journey into different sections. Let's first bisect this into a small triangle. Now, if I ask you, can you calculate the can you let me open the pointer again. Can you calculate the area of this triangle? As we know, it's quite easy. The formula is 1 upon 2 into base into height. So we have our base is 20, our height is 10, and so using these two quantities alone, we can calculate our area of the triangle, and that we would find out would be 100. So between 0 and 20 seconds, the car traveled 100 meters. How did we find this out? Because we know that the area under the speed time graph gives the distance traveled by the object. So by calculating this distance, we were able to figure out that by calculating this area, we were able to figure out that the car actually traveled 100 meters in this interval. If you want to calculate the distance for the entire journey, you can also do that, and the way to do that would be you can either divide this into one more rectangle and a triangle, or you can use this area that we have already calculated and calculate the area of trapezium here. Trapezium is a very useful shape in physics, because a lot of times our speed time graphs work in such a way that we can apply the formula of trapezium to calculate the area efficiently. If you're not familiar with the formula of area of trapezium, it is 1 upon 2 into sum of parallel sides into height. We will consider that formula in the future classes in more depth, and we will also look at while we are solving more past paper questions. But for now, if you guys want, you can go ahead and try this question. The answer that you should be getting is 350. But don't worry if you don't get it right now. We would look into more speed time graphs and velocity and distance time graphs in the future videos, so stay tuned for that. Our today's lesson was not too deep, because like I said, in O-levels specifically, it is very hard for us to stick only to kinematics and not also include dynamics into it. But from the next lessons, we would start looking at Newton's laws, and so that means that we would also start considering the forces, and in doing that we would enter our rather large field of general physics, and which is very important, and it is also a very pivotal part of physics in general. So hope to see you soon. Stay tuned, subscribe, and like the video. Thank you.